Len Bass tiene más de 60 años de experiencia.
We're going to
60
start.
años de experiencia.
We
Otra
have
vez,
Mr.
60 años
Len
de
Bass.
experiencia.
He's
Ha
got
sido
more than 60
consultor en
years of
proyectos que
experience.
van desde
He's been a
vehículos exploradores de
consultant
Marte. Ahorita en el almuerzo tuve la
to
fortuna de que contara la
exploring
historia de
vehicles.
cómo es que algo de su arquitectura pues, ha llegado hasta Marte. Y pues también ha estado en proyectos que van de sistemas automotrices. Ha escrito más de 100 artículos y libros sobre software, interfaz de usuario, arquitectura de software, DevOps e ingeniería de IA, que hoy y desde hace mucho tiempo hacen parte de la formación de miles de arquitectos en todo el mundo. En esta charla nos va a hablar de cómo diseñar sistemas de inteligencia artificial desde la arquitectura, integrando buenas prácticas de DevOps. Now, I would like you all to welcome Len Bass.
Let's welcome Mr. Len Bass. Ok, gracias. Me gustaría empezar agradeciendo a los organizadores de este evento. Ha sido muy agradable ver tantas personas interesadas en la arquitectura del software, la arquitectura del software, y me han cuidado muy bien los organizadores. A ver, hubo mucha discusión esta mañana con este tipo de citas. Cuando usted mira esto con el ojo de un arquitecto de soluciones, la primera pregunta que me viene a la mente: ¿qué es esa cosa de la inteligencia artificial? Entonces voy a empezar a hablar de la terminología. Este es el espacio de la inteligencia artificial. Dentro del espacio de la inteligencia artificial tenemos machine learning, que es razonablemente ya vieja. También tenemos dentro de Machine Learning dos categorías de cosas, lo que nosotros llamamos Narrow ML Models, quiere decir las antiguas. Y también tenemos los Foundation Models, que son la nueva tendencia, la nueva moda. Y dentro de la Foundation Models, tenemos Large Language Models. En adición, también tenemos la antigua inteligencia artificial, probablemente de hace 30 años, que tenía una configuración de reglas, y estas reglas, una a la vez, eran las de la inteligencia artificial. En esta charla voy a enfocarme en las Foundation Models, los modelos de fundación y la implicación de lo que esto significa. Entonces, estos son las Foundation Models, una forma de red neural. Es una de las cosas que yo aprendí trabajando con Daniel. Lo mencionó él antes. Hay mucho vocabulario. Una de las cosas que se trata son los neural nets. Esa es una forma de machine learning. Han estado allí en el mercado por mucho tiempo, pero no se convirtieron en foundation models hasta que las personas en Google descubrió de que ellos podrían hacerlos correr más rápidamente. El problema con los neural nets, que a medida que crecían y crecían, se volvieron un problema, y las personas en Google escribieron un documento en el 2017 donde dijeron que tensión era todo lo que se necesitaba. No sé cómo explicarlo, pero voy a meterme en ese tema más adelante. A ver, lo que sucede cuando usted tiene una foundation model, y ya que está entrenada en volúmenes muy grandes de datos, así es como se entrena. Si usted quiere utilizarla en una aplicación, eso es en lo cual el arquitecto de soluciones está interesado. Usted tiene que hacer una aplicación específica. Hay una etapa en el proceso que se llama customización. Voy a hablar de eso más adelante. Es donde usted hace el foundation model con el que usted está lidiando para poder entender el problema que usted quiere resolver. Y si usted mira
number of applications and the areas of those applications are growing. Your friendly chatbot is a foundation model. The machine
Chatbox es una foundation más, sí,
originally it wasn't. There are lots of applications. In the book we wrote, we have a case study where the application is understanding a request for proposals, finding the material, the bill of materials for that. So there are particular areas of application are growing, and lots of people are working on it. And so that's kind of the introduction to the terminology. But what's the architecture of a foundation model look like, or a system using a foundation model? I guess it's a question. And the answer is, well, you have the application layer, and the application layer talks to either an agent, so you have multi-agent types of systems, or it talks to a user directly. And underneath the application layer is the layer that does orchestration and acts as a proxy. Underneath that, you have a guardrail. You have the model serving layer. I put guardrails in with the proxies. And that's where the actual foundation model lives. And then you have hardware. And I'll explain these in a minute, or at least introduce them. So in the application layer, you have what the application does. You have a user interface. You have all the kinds of domain-specific knowledge that I shouldn't say it that way. You have the things that support the particular domain that you're trying to work in, and you have something called guardrails. So the thing about machine learning in general is that it's probabilistic. What that means is that you may run a system where you give the same input twice and get different answers because it's based on probability. And if you're building an AI system, that is one of the reasons why the AI system may fail to go into production, because that introduces an element of risk. If I run the thing in a test, it passes the test, I'm perfectly happy. I put it out into production and it does something weird. And you've all read in the newspapers the kinds of weird things that it might do. Sometimes the probabilistic nature is built in. We do not want to get the same answer for various reasons. And sometimes the probabilistic nature is because the thing isn't quite right. And then you also have guardrails. So you would customize the foundation model. The foundation model responds to a prompt. And the more specific the prompt is, the better the answer is going to be. So you've played with these things, I assume. And as you play with them, the more information you give it, the more it's going to answer or produce the kind of answer that you want. And so there are two techniques that are used for customizing. One is called prompt engineering, which means that I am going to take the prompt that you give the system is going to take the prompt that you give it, I should say, and add detail to it. And this detail may be in the form of just scripts that you've written, or it may be that the detail comes from something called retrieval augmented generation. So one of the problems in actually any technical field is that you have hundreds of acronyms, and at least at my age, you tend to forget what these acronyms are for. And so you live in terms of acronyms instead of in terms of concepts, and you internalize the acronyms. So RAG is the way that retrieval augmented generation, you can see it just rolls off the tongue, is used. And what that consists of is a database that the customization layer will access, and it has specific kinds of information in it relative to the domain that you're interested in. And I'll elaborate a little bit on that. A guardrail is a module. So we're looking at this from architecture perspective, so we have a collection of modules. A guardrail is a module that prepares the input, make sure that you're not giving it malicious input, or you're not giving it input that it doesn't want to answer. And it looks at the output, making sure that the output doesn't provide information that you shouldn't have for various reasons. I'll talk about that in a minute. Or that the output makes sense. Okay, so you can see that a guardrail, for example, might be a narrow machine learning system. And it looks at the output of the foundation model, and it says, does this make sense according to this other criteria? So the guardrails can get quite complicated. So moving on to the proxy orchestration layer, again, you're software architects. A proxy is something that translates, that acts as a translator from one notation to another, if you will. So a proxy takes input in one format, translates it into another format, hopefully semantically equivalent, and this gets important because in many contexts, these foundation models are evolving very quickly. So you have a code generation model, and the code generation models a particular version of a language. A new version comes out. What are the changes associated with that version? That's a nice picture. What are the changes associated with that version? What is the model? Do I have to change my application? Does the interface change? All of these questions are managed by the proxy. So whoever's in charge of the proxy will decide. And an orchestrator is just the same as an orchestrator in any other computer science kind of context. It decides on the order of operations. It decides on who gets to go. It decides on things like threading, model, and so on. We heard talks about that kind of thing. So this just says what I just said. So the proxy can act as an access control. So one of the concerns that I'll talk about in a minute is privacy. You have something that is trained on massive sources of information, some of which should not be available to any random user. So you need to do access control. And that gets a little bit complicated when I talk about privacy. But that would be done in the proxy. The other thing that gets done in the proxy is monitoring and logging. So one of the architectural concepts that is involved in machine learning is the idea of, is the answer make sense? Is the answer right? Why did I produce this? Why is an observability issue. But this answer was produced in response to this particular question. And that could have legal ramifications. And it could be controlled by regulators. And so in the application, in the system structure that I talked about, the model is not going to log itself because it doesn't know what the queries are. You log it, the proxy would log the information and the responses. Also does load balancing. Okay, so a lot of this should be familiar from talking about how the cloud works. So that's what an orchestrator does in the cloud. If you think about container management, then the orchestration, the runtime engine for the container management, orchestrates things. It decides on whether something's working. Did it break? Does it need to be replaced? How many requests do I have? How many services do I need? How many instances of the services do I need? Okay, and all that is done in the proxy monitoring layer. Okay, so this is the model versioning problem, and you route it. And it may be that you want to keep multiple versions of the model around. So again, let me use the code generation thing. I have a model that generates version A of a language, and version B comes out. And maybe I want to use version A, and maybe I want to use version B, depends on the application context. And so this one may have both models involved. And so this is done by the proxy layer. And observability is the other side of monitoring. So one of the things I'll talk about in a minute is when you're doing machine learning, especially with foundation models, there are a number of quality attributes that are going to be different. And one of them is observability becomes much more important. Not that these things weren't around, but if you look at a non-AI system and you ask what the important quality attributes are, it's going to be performance, it's going to be security, it's going to be maintainability, it's going to be availability. Those are the four big quality attributes. If you ask that of a machine learning system or a foundation model, it's those four plus some others. Okay, and I'll talk about the others in a minute. Okay, so the model server is where the magic happens in the foundation model. And the model server has two parts. It has the attention mechanism, and it has a vector space manager. So the knowledge base that it uses for doing its inferences is based on vector spaces. So I told you that the model might be trained on millions or billions of, or trillions of data items. Those are parsed in a certain way, and they get turned into vectors. So a vector is a multi-dimensional string of numbers. Okay, so now, if you remember back to your linear algebra course, which I can't, but you're younger than I am. In a linear algebra course, you learned about vectors. And in two space, a vector defines a line. In multi-dimensional things, it defines a line going through multiple vectors. Okay. And so the vector space, the knowledge base, is constructed by as a vector space. And the vector space is a multi-dimensional parsing of the input. And it isn't exactly right to think of the input as being broken into syllables. It's a little bit more sophisticated than that, but that's a good way of thinking of it. You take these tens of thousands or millions or trillions of documents, you look at each sentence in there, you break the sentence into syllables, you turn these syllables into vectors. And so what you get is a multi-dimensional vector that represents a sentence, for example, and the words in that sentence. And when I say multi-dimensional, it may be in the tens of thousands. Okay, so this knowledge base, this vector space, consists of words and their position in this 10,000 dimension space. Okay, or maybe it's less than that, or maybe it's more than that. Okay, so that's one of the numbers that keeps changing as the technology evolves. And then you have the inference engine. I can't read the slides.
Oh, okay. So, yeah, just...
So we have a trade-off here. The trade-off, on the one hand, is that the stand has a better audio thing than the microphone. The microphone's pretty loud. That's the one side of it. The other side is that I don't see as well as I used to. And so they show me the slides here, and I can't read them from over there. So the vision side won in this particular trade-off. If 20 years ago it would have been different things. So anyway, the inference engine consists of the attention mechanism. And so this is where the magic happens. The attention mechanism is a way of searching the vector space. So we have the vector space, which consists of the input, the attention mechanism, which is neutral with respect to the input and gets its input from the knowledge thing. And the attention mechanism involves matrix. So we have these vectors of 10,000 or however many. I multiply them. Okay, well, multiplying a 10,000 dimension vector by even another 10,000 dimension vector, or 10,000 by 10,000, gets to be complicated. And so what has evolved over the last several years are a collection of chips that understand how to do matrix multiplication where the matrices are very large. So chips that could do matrix multiplication have existed, but they were assuming that your matrix is size 100 or maybe size 10. If I give you a size 10,000 one, then you're talking about specialized hardware, and all of the AI people, well, I shouldn't say all, many of the AI people are working on developing chips that can support this type of activity. Okay, so those are the pieces, right? We're architects. So pieces have to be deployed. So where do they sit? So you have an expense associated with where things sit. If you have a piece of the system that runs on your laptop or on an edge device or an IoT device of some sort or a smartphone, that's going to be cheap to operate. If you have a piece that runs in the cloud, now you're at the mercy of AWS or other cloud providers, you understand. Okay, so when you put things in the cloud, there's a cost associated with it. And one of the ways that you manage the fact that there's a probabilistic nature to these things is that you may run them several times. Let me run a foundation model on a particular input, see what I get. Let me run it again, see what I get. If it's the same, I'm happy. If it's not, maybe I take some sort of average, although it's text, so it may be text, so average isn't quite the right word. And that runs up the cost. Okay. And then the model serving, so the proxy and the orchestrator live either in the cloud or on the laptop or on a server. And then the actual model serving is done in the cloud. The knowledge base is too large to keep in a normal laptop. And so you need to have massive amounts of storage. So you might think about this in the evolution of computers. When I started doing computation, which was a long time ago, the essence was performance. Everybody worried about performance. A secondary essence was memory. And then a third type of consideration was disk space. And those considerations led to the year 2000 problem, which those of you that are what is this, 2025? Those of you that are over 35, well, those of you that are over 45 probably remember. And there's also the network issue. So networks came about in 1970s, and sending things over the network used to be slow. It's gotten faster and faster, but the closer things are to each other, the faster it's going to go. And so all of these lead to saying that the model serving is going to be done in the cloud. They can optimize the positions, they can optimize the CPUs, they have massive amounts of storage, and they're pretty fast. Okay, so let me move on, talk about quality attributes. So we heard something about quality attributes this morning. Quality attributes exist for AI systems, for foundation model systems. And the definition of a quality attribute is that it is a measurable and testable property of a system that tells you how good the system is. Now that's a little bit, not totally correct in the sense that you can't always measure things, or the measurement is impractical. So if I tell you that my system has however many nines of reliability, how do I test that? I run it for a year and see how many times it fails. Okay, well that's an awful slow feedback loop. And so what happens is there are proxies for some of these unmeasurable qualities. And the standards in terms of qualities, and so when we started writing software architecture in practice, I think there were 20, maybe 25. And the number, so I don't know about Spanish, I don't know. But English is a very good language. If you want a new quality attribute, you put ility at the end. Is there an equivalent in Spanish? So you can generate as many quality attributes as you want, and they should have some meaning. And so one of the things that came out of this morning, if you were paying attention, is that the quality attributes that you choose to emphasize, remember the teeter-totter? It's all a question of trade-offs, and the trade-offs involve the business goals and the regulations and so on. And that's equally true of the quality attributes associated with foundation models. So there are really three issues associated with quality attributes. There's sort of vocabulary, there are some nuances, and there are some that have risen in importance. Not that they didn't exist before, but they've risen in importance. So vocabulary is a good example. If I talk about performance, and I'm a software engineer, I think in terms of latency, I think in terms of throughput. If I'm a data scientist and I use the word performance, I'm talking about accuracy. How good is the prediction? And if I'm a DevOps engineer and I talk about performance, I'm talking about cycle time. So DevOps is something that emphasizes deployment time. How long does it take something to get into production? That's the cycle time. And so performance from a DevOps perspective is cycle time. So the same word means different things. What happens is that you end up having teams with multiple disciplines. So you have software engineers, you would have data scientists, you might have a DevOps engineer, maybe not. And so it's a multidisciplinary team, and there's a theory that goes back to the 1950s, I think, about multidisciplinary teams. They go through four or five phases, depending on who you talk to. So there's the foreman phase. So you form the team. There's the storeman phase, where they argue a lot. What does that word mean to you? And that can last a long time. And that takes a lot of human capital, I guess, in order to get through that to the next phase, which is the Norman phase. Again, these are all ing words, but they're pronounced without it. The Norman phase is, we figured out what all the words mean. Now we have some norms, and let's make sure that all the teams understand what the norms are and use the words in their right context. And then there's the performance stage, which means let's go actually do something. So if you build, another reason for the 80% thing is if you build a AI system, it's inherently multidisciplinary. And it is going to take the team some time to learn how to work together. And so that's a time sink. Okay. So the vocabulary is going to change depending on what discipline you come from. There are also control issues, but that's a separate thing. And there are nuances associated with that. So security in a non-AI system means, can somebody hack into the system? Okay, and so there's a notion of an attack vector and an attack surface, and usually it's associated with network connections. When you move to the AI system, you can violate the security of the system by changing the training set, providing input that isn't accurate as part of the training, by sending it information, because these things will learn from the input queries that they get. So I know of organizations that built their own foundation models, which is a terribly expensive, time-consuming operation, because they wanted to ensure their intellectual property was not incorporated in one of the commercial foundation models. And so the notion of security can include controlling what goes into the input. They also had one set of input on-premise, and that would be done with laptops or local servers. And another, then they would use a commercial cloud provider, but the guardrails were always on-premise. And if they were using RAG, then the database was always on-premise. And so there are concerns about intellectual property and security that don't exist in non-AI kinds of systems. Reliability, another word that has different meanings. So reliability in the normal software engineering case is how many times does the system fail over a given period of time. So it's related to availability. And what do I do if it fails? In the AI sense, reliability is related to how correct are the answers, how much trust can I put in the answers, and there are metrics that talk about that. And then there are other quality attributes that have gotten more attention, more influence, more important because of AI. So observability is one. Why did the system do what it did? You turned on my credit. I wanted to get a mortgage. You turned it down. Why? And then the person at the other end will say, because the computer told me to, which isn't a very satisfactory answer. So observability is important, more important. The approaches for enhancing observability are using the monitoring and the logging facilities and paying attention to the training data. So the training data represents in some way or another, even when it's millions and billions of documents, represents in some way or another the kinds of queries that you expect the system to use. So you would train, for example, a chatbot with a different set of training data than you would with a code generation. It's a different domain, it's a different set of concerns. It would look for different things. There's also privacy. So privacy is one of those things that's starting to be, not starting, has been regulated. So the GDPR it has privacy concerns. The state of California has privacy concerns. And there are a set of rights that you have as a consumer. You have the right to know. The one that's interesting is you have the right to be deleted. So all of a sudden, this knowledge base that I had, which is this vector space, I want to go through and eliminate all references to Dario. Not that that would make any sense, but I might. Okay. So I have to be able to retrieve in the vector space all of the references to a particular individual and eliminate them. And they existed in a sentence, and so there were words around them in the sentence that may have been influenced, whose vector may have been influenced by the word that the person that you want to delete. So it gets fairly complicated. Access control. I'm a doctor. I have the right to get into health records. You're one of my patients. I have the right to look at your records. You changed doctors. The model doesn't know that. The knowledge base doesn't know that. And so I no longer have the right to look at your record because you now have a different doctor. So somehow I have to be able to put that into the system somehow so that it will eliminate you while it's doing access control for any references that I make. Okay, so all these are fairly subtle kinds of things that are enshrined in California law and again in the GDPR and I presume elsewhere. And those are things you needed to worry about. So that's more privacy. Guardrails are important in privacy. So the access control for the examples that I gave you would be done in a guardrail. And it would have to know which doctors in the healthcare, which doctors had which patients and had access rights for which patients. So reliability, again, is how much do I trust the answer? And this goes to the training set. So you need to make sure that the training set for the model that you're using is broad enough to cover the cases that you want it to work on and deep enough so that it has sufficient information to be able to analyze it. Okay, so there's a breadth and a depth requirement. And to me, that's a research question. How do you measure the breadth and depth of a training set with respect to a domain? You have to define the domain in some formal sense. You have to be able to look at a training set and decide how it corresponds to that particular measurement of the domain. And again, there are ways of improving that, and it has to do with the training set. And you know, one of the techniques you use for reliability is exactly the same technique you would use in a non-AI system. How do you achieve reliability? You have redundancy. I would have 2 instances of the same service somewhere out in the cloud. If one of them fails, which I can recognize because it doesn't respond, then I switch to the other one. That's the standard mechanism inside the cloud. I would have 2 models. I could give the same query to both models. And again, you know, you get into the variations of reliability and availability. And finally, we have security. So I said a little bit about this. So security, in a simple sense, is CIA. Confidentiality, integrity, availability. So confidentiality says that no one that isn't authorized can get to it. Integrity says once no one that isn't authorized can change it. And availability means those people that are supposed to be able to access it can. So that denial of service is a way of breaching that kind of service. So what's grown up in the non-AI world and what you can apply to the AI is the notion of zero trust. So it used to be that that people used what's called perimeter security. And so you had an outside perimeter, so you want to break into a house, right? How do you break into a house? So first you have to get over the fence, that's the outside. Then you have to get by the guard dogs, that's the second level. Then you have to breach the security mechanism on the windows. And then you're finally inside the house, but it turns out there's a sensor detector or something. So that's one form of defense based on perimeter. So the assumption is that if somebody gets through those, that they're legitimate. With zero trust, in theory, every request is validated. So maybe the AWS people can correct me on this, but there's something like 400 million IAM requests in AWS per second. And I'm not sure the number, and I'm not sure it's per second, but it's some fantastic number because every request that you make and that is a result of your request goes through an IAM mechanism. And so that's a phenomenal number. So zero trust says that. There's also the notion of process. Let me define the ways that somebody can attack the system, and I do that by having a bunch of people or maybe AI agents tell me what the attacks are. What's the attack surface? How do people attack it? And there are systems that do this as well. And so that's another facet of security. I want to leave time for questions. So those are there are a list of major attack types. And you can see them here. So these slides are available somewhere, and I'm going to put them on the internet. You can, anything that I skip over here, you can look up. And here's a list of attack vectors. And there are various approaches for security. And the approaches that are different with foundation models than from regular systems are based in guardrails. Okay, so this all comes from a book that some co-authors and I wrote. How big is it? Oh, it's a big QR code. So if you use the QR code, it'll take you to the publisher's website. And then you enter the magic code there, and you get a 35% discount. So I've written a bunch of books. Some of which were published, most of which were published by a publisher, one of which I self-published on Amazon. So there are pluses and minuses if you want to write books. There are pluses and minuses between going through a publisher and self-publishing. The publisher has a variety of advantages. They market your book, whereas on Amazon you don't. They have people that do proofreading. So if you look at the one I self-published, I'm sure you can find some typos. They have people that make up indexes, and they get it reviewed. So there are a number of advantages of going through a publisher. The disadvantage is that the publisher sets the price. So the price on this book, I think is somewhere in the order of $40. I don't know. I haven't had to buy it. The price on the one that I self-published, which is the textbook I use for the course in deployment in DevOps that I teach, depends on the form you want. If you want a paperback, it costs you $15. If you want a Kindle, it costs you $10. And if you just are happy with a PDF, it's free on the net. So, that's the advantage of self-publishing for those of you that want to write books. Okay, so I'm open for questions. Oops, I went the wrong way. And I want to thank the sponsors. I'll leave this one up. So if you're not tired of the sponsors, finding out who the sponsors are, you can see it again. Question.
I have a question regarding which is going to be the approach of the companies with the emerging attacks directed by AI. So,
give me a for instance.
Like, let's say that a company is being attacked for an AI agent, and which will be like the barriers that the companies must have to be able to protect the environment.
So we have a couple of case studies in the book. One case study is a company that wanted to use language matching to do fulfillment of procurement requests. So you're going to build, I don't know, a room. Well, a room needs chairs, a room needs various types of air conditioning, a room needs rugs, and so on. So you would put out, if you're a company that's going to build a room, you would put out a request for proposals, and the people that make chairs and rugs and all the other kinds of things would bid on it. And this has been a manual process, and so the case study describes how that got turned into a foundation model. So that's one case study that might be of interest. The second one is in Australia, there's a company, a nonprofit organization whose job it is to technify, I'm not sure there's such a word, to encourage Australian small industry to use the latest technology. They have a service that they offer to small companies to produce chatbots. So you want to do a chatbot, you're a small company, you provide them with the information they need, and they will produce for you a chatbot. So there are a variety of different business models that you might find.
Thank you.
Oh, no, somebody's waving over there. Anxious question. Oops.
Hello. I have a question regarding observability.
Okay.
So you can build everything into your system, have your observability and traceability, except for the foundational model, right? Which is kind of a black box, unless they provide that observability. So do you think that in the future, this will become a requirement for foundational models?
Okay, so part of these qualities depend, if you're dealing with a commercial foundation model, part of these qualities depend on what the producer of that model provides. So one of the more interesting things to me, not a direct answer, is the weights that come out of the vector space. So these words all have weights that position them. That's held by the company. There is a public, an open source one, but in general, the AI companies keep that information proprietary. Observability depends on the vendor making that information available. And that depends on consumer pressure. Right? So it's like any other function that you want from a commercial system. If enough customers ask for it and say, this other system provides it and you don't, I'm going to use this other system. But in general, you're at the mercy of the vendors. Other questions?
You talked about reliability, and my question is, as I understand it, it is mainly achieved within the creation of in-house models, right?
It's mainly achieved within the region of,
The creation of in-house models.
oh, it's creation of the models?
So my question is,
Yes,
how
and-
does one achieve reliability using commercial models?
Yeah, so I guess my response to that would be yes and no. There is the notion of ground truth. So if I ask how many people are in this room, the foundation model may come up with an estimate, but if I really wanted to know, I could count. So that's the ground truth. And so there are metrics where you measure the prediction of the system against ground truth to get some measure of reliability. So it's a little more nuanced than that. I think I ran out of time. Well, thank you for your attention.